Connected bodies. If a system involves the motion of more than one particle, the particles may be considered separate. Particular care is needed to ensure that all the forces acting on each particle are considered. That is why it is really important that you draw a precise, neat diagram highlighting all the key forces acting on a particle. But if the two particles are acting in the same straight line, moving in the same straight line, then you can also treat the whole system as a single particle, meaning that you can combine their masses, you can assume that their acceleration is the same in both parts, and that you can assume, and in some situations, you may be able to ignore certain unknown forces. For example, quite often, like this example we're going to look at, you may be able to ignore tension in the first part if you consider it as a whole connected body. So, two particles P and Q of mass 5 kilograms and 3 kilograms respectively are connected by a light inextensible string, even though it says strong. Particle P is pulled by a horizontal force of magnitude 40 newtons along a rough horizontal plane. The coefficient of friction between each particle and the plane is 0.2. The string is taut. Firstly, find the acceleration of each particle. Right, before we do that, as I said before, it is vital that you draw a diagram. So, for this question, we know that we've got particle P of mass 5 kilograms and we've got particle Q of mass 3 kilograms. Right, we're also told it is on a rough horizontal plane. So there's our horizontal plane. And obviously, acting downwards is going to be the weights of each particle so it's the mass under the force of gravity, so 5g and 3g, and acting upwards will be a resultant force of 1 and resultant force of 2. Now we're told that P is being pulled along by a force of magnitude 40 newtons, so 40 newtons. We're also told that these two particles are connected by a light inextensible string, and there must be a tension. Those tensions will be the same. Also, because it's a rough horizontal plane, we have to take into consideration friction, and the frictions will be different for particle Q and particle P. We're also told that the coefficient of friction is 0.2. That is everything we are told from the information. Now first it says find the acceleration of each particle, which is the only other thing I haven't highlighted on the diagram. Now, because they are connected by a light by an inextensible string, we can assume that the acceleration is the same for both particle P and Q. So, what we are going to do is we're going to model this as one entire particle, and if we do that, we can eliminate the tensions. But we do have to still take into consideration the friction on P and on Q. Now to do that, remember, we have to find out what the normal reaction force is for both P and Q. So if we look at P over here and Q over here, if we take forces upwards, then F equals ma. We've got the force, which is our normal reaction R1, minus the weight 5g equals 0, because there's no acceleration upwards and downwards, which means R1 is equal to 5g. And if we do the same for Q, remember, using F equals ma, we've got R2 minus 3g is equal to 0, which means R2 is equal to 3g. Right, so now we know that our combined particle is going to be moving in this direction. So we're going to combine these two masses to make 8 kilograms. We know now what our we know what our normal reaction is, so we can find out what the friction max is for P and Q by timesing them both by 0.2. And as we're going to combine them as one whole particle, we're not going to have to worry about the tensions in the middle. So let's now finally, as we are travelling in this direction, let's find the force in that direction. So in that direction, we've got the 40, and then opposing motion is our F1, which is 5g times 0.2, the coefficient of friction, and also opposing motion is the 3g times 0.2. And we're asked to find acceleration, remember, and we know that the combined mass is going to be 8 times the unknown acceleration. So if we tidy this up, we get 40 tie away 9.8, that's 5 times 9.8 times 0.2 minus 5.88, which is 3 times 9.8 times 9.2. Collect together the numbers on the left hand side and you get 24.32 equals 8a, which means the acceleration you divide through by 8 is 3.04 ms to the minus 2. Now remember what I said, because we're told it is an inextensible string, the acceleration is the same in both parts. So the acceleration on our diagram now is 3.04 ms to the minus 2. That's part 1 done. Part 2 says find the tension in the string. Now the tension is going to be the same whether you looked at particle P or particle Q. So let's look at the tension around particle P. So we're now just going to take into account particle P. So this is part B. So just looking at particle P, and we'll still take the resultant forces in that direction. So we look back at our diagram, we've got the 40 acting in that direction, and acting against it is the tension and the friction. So we've got 40 minus 5g times 0.2, which is your friction, minus the tension. Now we know what the acceleration is now because we found it in the last part, so it's going to be just 5 now times 3.04. It's only 5 because we're looking at just particle P. So if we tidy that up a little bit, we get 40 minus 9.8 minus t is equal to 15.2. You rearrange this equation a little bit, add the tension to both sides and subtract minus 15.2 from both sides. You have this. If you sort that out, you'll find that the tension is equal to 15 newtons. And as I said before, if you took the forces around particle Q, you should get the tension also as being 15 newtons. Right, part C says explain how the modelling assumptions that the string is light and inextensible has been used. So I'm not going to write these down, I'm just going to say these. So inextensible. Now remember, if you can't remember these modelling assumptions, you need to go back and look at chapter 1, which is a list of all the assumptions that we're making during Mechanics 1. And sometimes in exams you are asked these, and they're usually just 1-mark questions, but it's worthwhile knowing. So inextensible, we're assuming the acceleration of the masses is the same, and the light means that the tension is the same throughout the length of the string, and the mass of the string is negligible. So there's very little mass in the string.